Well, hello. This is Chapter 11, Part 1 from your Essentials of Radiographic Physics and Imaging book, and this chapter begins on page 130. This chapter is about radiographic exposure technique, so kind of taking all the components of things that we've talked about so far, talking about the fact, so far we've led up to the fact that milliamperage in time, or our mass, affects the quantity of radiation that gets produced in the X-ray tube, and how kilovoltage actually affects both the quantity of photons produced and the quality, or the penetrating ability and average energy of those photons that get produced. And then we kind of spoke about how our image is supposed to accurately represent the anatomic area of interest, and understanding the concepts of brightness and contrast, spatial resolution, distortion, and the noise that can take place. So getting us to understand what components make up a quality or diagnostic or optimal image, and how our manipulation of the exposure factors can affect that. So in this chapter, we are going to talk about how it's our responsibility to select the combination of exposure factors in order to produce a quality image. And we need to know and understand how the factors actually will affect the image. We've already talked about how some of these factors will affect the patient and what happens in the patient. So understanding that how we manipulate them will affect our final results on our image receptor. And as always, the goal is to expose patients to the least amount of radiation necessary in order to produce that diagnostic or quality or optimal image. And by that, we always want to adhere to the ALARA principle, which is as low as reasonably achievable. That is always our goal anytime we take an image. So when we start off looking at this, they start off looking at the primary factors, and typically the primary exposure factors are things that we typically select on the control panel. And we select things like our milliamperage, our time, our KVP, and realistically, depending on what kind of control panel we actually have, we're either selecting separate milliamperage and exposure time, like in room 1, or it could be that you're just choosing a combined factor of your mass overall, kind of like we have that capability in room 2, and a lot of our clinical sites, you're just simply selecting an overall mass value and deciding if you want small or large focal spot. So regardless of how the control panel is, it's important to understand what each factor actually controls and how we manipulate it, what that does. So a lot of this is going to be reiterating what we've already discussed, again, because it's kind of rehashing some of the things just to drive the point home. So milliamperage and exposure time, when you multiply those two together, that does give us our mass value. Remember that our mass is directly proportional to the quantity of radiation that reaches the patient and affects how much remnant or exit radiation there will be reaching the IR. Mass, or milliamperage in seconds, is inversely related to exposure time in order to maintain exposure to the IR. Meaning, if your milliamperage goes up, then your time factor would have to go down in order to maintain your exposure. And the opposite would hold true as well. If your milliamperage went down, your time factor would have to go up in order to maintain your mass value. All they're saying with that is simply that the equation, in order to keep your mass equivalent, your exposure equivalent, you would have to raise one and lower the other, if that was an option, or if you were forced to do that. Maybe to minimize motion, you raise the MA station so that you're able to lower the time. Okay, and again, we've seen this image before, but when you have less mass, you have less quantity of photons in this primary beam because you had less electrons released from the heated filament. So when you have less photons striking the patient, you're going to have overall less exit radiation, versus when you raise the mass value, you have more photons striking the patient because more electrons were released from that filament. which yields more exit or remnant radiation. Also with mass, as far as exposure time, it is directly proportional to quantity. It's directly related to our exposure, and it's inversely related, like I said, to the MA station in order to maintain your IR exposure. MA times your time, which is always given in seconds, and realistically it's milliseconds, equals your mass. And there are all kinds of variables that can actually affect the amount of mass that you need in order to produce a diagnostic image. There are patient factors, there are equipment factors, image receptor factors, all kinds of things that can affect that. And most of that comes with time in the field and learning about different patients and actually making exposures on real patients and visualizing what happens once those exposures are made. They also reference that digital IRs have a very wide dynamic range, okay? Meaning that the digital IR can detect a wider range of radiation intensities, meaning when that energy comes out of the patient, anything that strikes that image receptor, it basically can record that radiation intensity as a shade of gray. So it has a much wider dynamic range. So it's not as dependent on the mass value as, let's say, our film image receptors were. All right, film was very mass dependent, but digital is not as much dependent on the mass value as film was. But they do say that, you know, exposure errors still can adversely affect the quality of the digital image, and that's what we're going to talk about. The image brightness, which basically is what your mass helps to affect or control. Image brightness is adjusted during the computer processing, meaning it's not something that we actually do. So it gets adjusted during computer processing, and it'll compensate for low and high exposure errors. And this is a point processing function called automatic rescaling. So it automatically rescales the image to display the appropriate amount of brightness as best it can. So that is something built into the system. It is not something we control, but it tends to lend itself to making for more apathetic text, because this is where it's important to look at your exposure indicator values to know that if you are properly exposing the patient, not overexposing the patient, not underexposing the patient, because the computer can make the adjustment. Now, the point processing function called automatic rescaling, we have not talked about that yet, and it is not in this chapter, but I did want to let you know that that's what it's actually called, is automatic rescaling. And it's a point processing, meaning it happens before we see the image, where it adjusts the image brightness to appear appropriate, kind of regardless of what our mass value is set at. So if it's too low, it'll still appear appropriate. And if it's too high, it'll likely still appear appropriate. But these exposure errors can result in increased quantum noise or an increase in patient dose. If we look at the bottom of page 132, they show you two hip images, two right hip images, and picture A is an image that was created using a sufficient amount of mass. So you can see that you can make out bone trabeculi, you can see the head of the femur sitting in the acetabulum, you can make out the greater trochanter, you can make out the changes in the bone of the femur, the proximal femur. Can make out the ilium very clearly, the ischium and the pubic bone. We can see the sacrum in here and the bottom of the lumbar spine, like L5 where it meets with S1. So this is sufficient mass, and this is a diagnostic image. Whereas picture B, there was insufficient mass, meaning they did not use enough which allows it to present as quantum noise, meaning you can kind of make out, and probably in your book you can see a little bit better, this speckled or grainy appearance. And remember, quantum noise is where there's an insufficient quantity of photons striking the image receptor that doesn't allow for a full image to appear. So it appears grainy or speckled. And the only way to correct quantum noise is to increase your mass value, because remember, quantum noise is photon dependent, meaning that image is created when the photons exit the patient and strike the image receptor. And if you don't have enough photons striking that image receptor, it will appear as this speckled, grainy appearance, and it takes away from the image quality. You haven't over-radiated the patient. In fact, you've under-radiated the patient, which from that standpoint is not as bad as over-radiating them, but the image is not diagnostic, so you would have to go back and repeat, which means you've added more radiation dose to the patient than you would have had you used the appropriate mask the first time. Okay. In general, I will tell you that when you have to repeat an image because of an exposure error, the minimum change is typically you adjust your mask by a factor of 2, meaning the minimum change required would be to minimally either double or half your mass value. All right. That's the minimum change. You can go more than that, but the minimum you should do is at least double your mass or half your mass to start with. Also, when they talk about some of these exposure errors as far as appearing acceptable, on the top of 133, we can see how our exposure errors affect our image brightness. And they give you 3 pictures of a right knee, right? And picture A was created with sufficient mass, meaning this was the appropriate technique that is considered diagnostic or optimal or a quality image. And if we look at B and C, they truly don't look very much different from picture A. But picture B was created with insufficient mass, so there is an amount of quantum noise visible. And again, not so much on this PowerPoint is it present, but if you look in the book, the picture is a little bit better, a little bit bigger, so it's easier to see that there is some quantum noise in this image because there was not sufficient mass used. In picture C, they used excessive mass, so they don't have the issue of they don't have the issue of quantum noise, but the problem with this is because you've used so much mass, you've over-radiated your patient for no reason, because our image doesn't look any better. In fact, they all look relatively the same. So that's when I'm telling you that the point processing function of automatic rescale can take insufficient and excessive exposure errors and still make it appear appropriate. Now that's kind of a good thing because we might not have to repeat as many images, but the downside is with this, you've taken away from the image quality because you've got too much quantum noise. And with this, your image looks okay, but you basically have fried your patient. Okay, so digital is good in the fact that it can save a lot of things. It can save us from having to repeat a lot of images, but it also gives a false sense of confidence to the technologist that they're doing things correctly when the images appear correct, because they might not actually be doing it correctly. Okay, so in order just to finish up with mass, again, if there's an error based on exposure, meaning not enough or too much exposure, the minimum change is that you typically adjust your mass by a factor of 2. So you either double or half your mass value. All right. And then if there's some other kind of error that is because of positioning error or motion thing along that lines, then you can make an adjustment in the exposure to produce an image of diagnostic quality. And typically with that, even though we haven't gone completely over it, if there's another error present, typically a repeatable error, meaning that the patient moved you put them in the wrong position. There's artifact on there that obscures the anatomy and you have to do it again. If there's a repeatable error and your exposure is not sufficient, maybe it's just a little bit too dark or a little bit too light, then you can adjust your mass value by at least 30% and make that change in exposure because you have to repeat the image anyway. All right, that's called the 30%. The 30% change, because we've discussed before that in order to see a visible difference in your exposure, it requires a minimum change of 30% in your mass. So if the error is that your image is simply too light or too dark, then you have to adjust your mass by a factor of 2. But if there is some other repeatable error and you don't really love the image because it's just a smidge too dark or a smidge too light, then you can correct the repeatable error and make the mass adjustment by raising or lowering it 30% and make the repeat image. Okay? And those all have to do with exposure errors. But now we're going to move into talking about KVP and some of the errors that come along with that. All right, so KVP affects the exposure to the IR as well, because remember, it alters not only the amount of radiation exiting the tube and entering the patient, but it also affects the penetrability of the beam and how it passes through the patient. It determines, is it going to transmit, is it going to photoelectrically absorb, or is it going to create Compton scatter? So it alters the amount and the penetrating ability of the beam, and it affects the amount of radiation exposure to the IR. So it also plays a part in exit or remnant radiation. When we look at kilovoltage, they show you an emission spectrum on page 134, and how the fact that when you change your KVP, like the green represents 72, the pink represents 82, and notice that there's a change on the emission spectrum in quantity, because the 82 is higher at all levels on the y-axis. So it's greater quantity. And not only that, but the peak of the emission spectrum, which represents the average energy. Notice the peak at 72 is right here, and the peak at 82 is just a little bit to the right of that, which means it has higher average energy. It just is more higher quality with regard to a raising KVP, and higher quantity as well. And just it intersects the x-axis at 72, and this would intersect the x-axis at 82. So increasing KVP not only increases your quantity, but it increases the average energy of the beam as well. When we talk about how KVP affects our digital image, it's similar to the effect of mass on the digital image, meaning if you have too much radiation reaching the image receptor, you're going to produce an image that will appear with the appropriate level of brightness because of that computer processing, but you've overexposed the patient. Okay, so too much KVP, your image will look appropriate, it will look acceptable, but you've over-radiated the patient. If you use too little radiation reaching the IR, again, your image will appear appropriate, but you could cause an increase in quantum noise, which will take away from your image quality. So KVP affects the exposure on your digital image similarly like mass does. So again, using the appropriate amount is very important. And they give us some pictures of knees. Again, this is on page 135. So picture A, they used 70 kVp at 2 mass on this particular knee. Okay. In picture B, they used 50 kVp at 2 mass. So they dropped the kVp 20 full kVp increments. So what that yields us is typically higher subject contrast, but the computer adjusted to maintain the brightness. Okay, and in the book you can see some quantum noise in this because the photon energy was dropped. There wasn't enough photons striking that image receptor to give us as diagnostic an image. So there is some graininess in this middle picture. And then picture C, they used 93 kVp at 2 mass, which would give you lower subject contrast, but the computer again adjusted to maintain the brightness, but you've overexposed the patient. So just like with mass, these look relatively similar. You can tell this one is more, it's brighter than this one, which they did tell us it gives us higher contrast in this, which is true. And this one gives us lower contrast than the original, but realistically, to an untrained eye, these look very, very similar. Just like they did with our mass changes, the computer can make the adjustment so that the exposure appears appropriate even if it was not appropriate. So 70 kVp, 50 kVp, 93 kVp. Huge change. I mean, you've got 43 kVp difference between B and C, but they do not look that much different. If you were to take these images and use the same technique with film, they would be completely polar opposite. This would be pitch black, and the one where you used 50 would be very, very, very white, almost not even penetrated. But with film, you were stuck with whatever your control panel settings were. It affects film much differently than it affects a digital IR. Not to mention with digital, we can create computer programming that allows those adjustments to be made, whereas with film, whatever struck that emulsion layer, you were stuck with. You've heard me say before, with film, what you shot is what you got. With digital, way, way more wiggle room on that, way more room for exposure error and things to appear appropriate. With KVP, we typically do not manipulate the KVP in order to vary the amount of exposure, because we know that not only will it affect the amount of exposure, but it will affect your contrast. With KVP, we tend to use the 15% rule, which says that altering the KVP by 15% will result in the same IR exposure as if you were to double or half your mass. So if you alter your KVP by 15%, it would have the same effect on the exposure to your image receptor as if you were to double or half your mass. So then to maintain the exposure to the IR when the KVP gets adjusted, the mass would have to be changed by a factor of 2. Meaning, if you raised your KVP 15% in order to maintain the exposure, your mass value would be cut in half. And if you lowered your KVP by 15% in order to maintain the exposure, your mass would have to be doubled. So this is no different than what we've been working out all along, but all they're reiterating is that we usually don't change our KVP if it's an exposure error, because we know that our contrast will be affected as well. All right, then they give us 2 chest images on 136, and they tell us that when you alter the X-ray beam's penetrating ability, it affects its absorption and transmission, which makes sense because if you raise or lower the KVP, you're changing the wavelength and the frequency of those photons along with the energy. So when you have higher energy, it tends to transmit more, and it raises the chance of Compton scatter. But when you lower your KVP, you tend to increase the amount of photoelectric absorption. Okay, so with these pictures on here, they're showing us that this one, This top picture here, they used higher KVP. You can see the photon energies here are greater, more penetrability, shorter wavelength, increase in frequency compared to here. So when you use higher KVP and you increase the penetrating power of the X-ray beam, you end up with less absorption, more transmission. You also would get more Compton scatter. Okay, so this image would have lower subject contrast, meaning higher KVP, lower contrast, more shades of gray, and it gives you a long scale. On this bottom picture, they used lower KVP, so it decreases the penetrability of the beam, giving you more absorption, less transmission, less Compton scatter. So you end up with more variation in the X-ray intensities that leave the patient. So this image gives you higher subject contrast, meaning the differences between the adjacent brightness levels is more distinct. You pretty much have white and black. All right, whereas up here, it's not as significant a change, it's more subtle. So this represents lower contrast. High KVP gives you low contrast. Low KVP gives you higher contrast or increases your contrast. When you change the KVP, it absolutely affects the absorption and transmission, like we just said. So a higher KVP will reduce the number of interactions and increases the amount of X-rays that get transmitted. Okay, so higher KVP, more transmission, more Compton scatter, less photoelectric absorption. And the opposite would hold true as well. Lower KVP would increase the number of interactions, meaning you would end up with more photoelectric absorption, less transmission, less Compton scatter. And they also tell you that as far as contrast goes, it's very dependent on the type and the composition of the tissue that you're passing through, what structures you're trying to visualize, what anatomy you're actually looking at, and it says the diagnostician's preference. Now, the diagnostician is not really focusing on us, it's more what is the radiologist's preference. It does play some part as to what we like, but realize that you're taking that image for the radiologist to read and make a diagnosis. So if he or she prefers low contrast images on everything, then that's what we have to image for. That's who we're trying to please with that image. So it's not so much about what we like and what looks good to us, because we are not the ones reading those images. It's about what does the radiologist like and what does he or she prefer. Okay, so mass and KVP absolutely affect your exposure to the IR, but not as heavily as it did with film. There's a lot more wiggle room with mass and KVP and digital exposure, because there's computer programming that can allow things to look acceptable even when they truly might not be. When there's an increase in quantum noise, that is photon dependent, and that can only be corrected by raising your mass value. But it takes away, remember, from image quality. And over radiating your patient is never the way to go. So being mindful of those factors, even though the digital allows us more wiggle room in our exposure and the errors that we make, and it can still make things look acceptable, knowing what you did and if they truly are acceptable is vital to you becoming a competent technologist and really understanding what you're doing when you set that control panel. Okay, so those are the main factors that they talk about with regard to making our exposure to the IR. Those are the two biggest things that we set on the control panel. But there are also some secondary factors that come into play, and those begin on page 137. And those factors, which we'll go into a little bit, are your focal spot size. And remember, focal spot size always plays a part in your spatial resolution. Okay, that's pretty much the only thing your focal spot size affects is your spatial resolution. Remember that that is determined by a choice on the control panel, either your MA station or a separate selection. Remember, your focal spot size choice determines which filament is actually going to heat. All right. Okay, hang on 1 second for me. All right, so let's look at focal spot size first. Oh, I'm so sorry. Let me say the rest of those. So focal spot size, your SID, your source to image receptor distance, your OID, which is from the object to the image receptor distance, the alignment of the central ray, grids, beam restriction, the generator output, tube filtration, compensating filters, and patient factors. Okay, and we'll probably talk about the first few in this, and then the second portion we'll actually talk about grids and the rest of these. I kind of broke this chapter into 2 sections just because there's so much information. All right, so focal spot size. Again, we typically either select it when we select our MA station, or there might be a separate selection where you choose small or large focal spot. Focal spot size affects the sharpness in the image, so it only affects your spatial resolution. Remember, our focal spot comes into play with the line focus principle. Because the anode target is angled, it allows us to have a smaller effective focal spot, which gives us better spatial resolution on our image. And you always want to use the smallest focal spot size that you could. Ideally, we would only use small focal spot. But what happens when we do that? If you were to choose small focal spot for everything, your time factor would increase, which allows more room, more chance of motion, right? And you would be bombarding that target for a longer period of time, which would increase the heat factor in the tube and potentially shorten your tube life. So we don't choose small focal spot for everything. Sometimes we have to decide which is better, to sacrifice some of the resolution and get the image quicker because the patient's, a trauma patient or having a hard time holding still or in excruciating pain. Sometimes you opt to go with a large focal spot so that you can reduce the time factor. Typically, the rule of thumb is for extremity work, you use small focal spot because they're not having to hold their breath or anything like that. And for trunk work like chest, abdomen, anything that falls in those areas, we tend to use large focal spot because not that we're not concerned with the resolution, but there's so much anatomy in there that resolution is not your like your main factor of concern. But with extremities, it is, because usually with extremities, you're looking for breaks in the trabecular pattern. You're looking for small fractures and things like that. So rule of thumb is usually extremity work, small focal spot, trunk work, large focal spot. And they show you this, that where the object is, and when you've got a larger focal spot, you have room for more unsharpness, so you have lower spatial resolution. And with a small focal spot, you have less unsharpness, so you have higher spatial resolution. And that image is actually on page 137. Okay, your SID, which is your source to image receptor distance. And remember, your source is always the focal spot. So your SID absolutely affects the amount of radiation reaching the patient. Because the beam diverges, the farther you are from your patient with your source, the more the angle of divergence. The closer you are, there's less divergence. Okay, so they tell you that SID and radiation intensity or quantity are inversely related. And the inverse square law says that the intensity of the beam is inversely proportional to the square of the distance from the source. Right? So again, we know this information. It's just bringing it back to mind and reiterating these concepts of why we do some of the things that we do. So with regard to the SID, anytime we have a change in SID, we know that we typically have to alter our mass value because we have to alter the quantity in order to maintain the exposure to the IR. So with that, we use the direct square law, or the exposure maintenance formula, which basically you take your mass values, your mass 1 over 2 is equivalent to your first distance squared over your second distance squared. And it allows us to calculate what change in mass we need dependent on the change in SID. Now, you're probably not going to have your calculator on you and figure this out. So there is a really good rule of thumb that I wanted to point out to you, and that is on page 139. And it kind of goes along with this next slide where they tell you that there are standard SIDs that we tend to use so that there's more consistency in radiographic quality. It helps to accommodate for any equipment limitations, and typically those standard SIDs are 40 inches, 48 inches, or 72 inches. And again, anytime you change your SID, you have to alter, or you should alter your mass value, because if you don't alter the mass value, you're either going to under or overexpose your patient, okay? So that, with that said, before we talk about how it affects image distortion, if you look on page 139, in the left-hand column, in the first paragraph, almost to the end, it tells us that when you use a 72-inch SID, if you can't use that 72-inch SID, but you could go to 56-inch SID, then you could use half the mass value of what you would use at 72, and it would be appropriate. And if a 40-inch SID couldn't be used, you could again go to 56 inches and double your mass value. And they just give you that as a quick method to calculate the changes in mass in order to produce a sufficient IR exposure. So if you can't get to 72, you could go to 56 and cut your mass in half. And if you couldn't use 40, again, you could go to 56 and you could double your mass value. Okay, so just a really good rule of thumb to be mindful of, that 56 works either way. If you're supposed to be at 72, but you could only get less than that, then just go to 56 and cut your mass in half. If you're supposed to be at 40, but you can't for whatever reason, go to 56 and double your mass value, right? Just a good rule of thumb to keep in mind. And they also talk about that SID absolutely plays a part in our distortion and spatial resolution, because remember, the further away the source is, the more straight on those photons will actually strike the part. And the more straight on they strike, the better they image the anatomy. So you get improved spatial resolution and reduced distortion with a longer SID versus a shorter SID. Our other distance that plays a part also with distortion and resolution is our OID. Okay, and OID affects the radiation intensity or quantity that reaches the IR. It affects the amount of scatter that reaches the image receptor, because realize that when there's an increase in OID, these scattered photons have a chance to miss the image receptor. And if they miss the image receptor, then we don't get that radiation fog on our image, which is a good thing. It also plays a part. There is magnification when there's an increase in OID, which means that there is distortion. It's not a good thing. And it takes away from our spatial resolution, because remember, spatial resolution and distortion are inversely related. So if you have better spatial resolution, you're going to have decreased distortion. And if you have an increase in distortion, you'll have a decrease in resolution. Remember, all positioning is based on utilizing a maximum SID and a minimal OID, meaning you want the part that you're imaging as close to the image receptor as you can. And sometimes, even when it's right on top of the IR, some part of that anatomy is always going to be further away from the IR. So we do our best to minimize distortion. And remember, that positioning book is already set up so that someone has already figured out that if we use the maximum SID and we put the patient in a position where it's minimizing OID, whether that's PA or AP. I'll give you an example, like the chest x-ray. Chest x-ray is done at 72 inches so that the photons strike more straight on and it doesn't magnify the heart. Okay, we also do a chest PA versus AP because the heart tends to sit more anterior. So if you're facing the chest board and the image receptor is in the chest board and you're facing it, meaning you're PA, then your front is closer to the IR than if you were putting your back against the board. So by doing the PA chest, it puts your heart closer to the IR, which reduces OID, and you're utilizing a 72-inch SID. And then when we do a lateral chest, we do a left lateral chest because, again, the heart sits on the left. So if you put the left side closest to the chest board, then you're minimizing OID. So that entire positioning book is already based on maximizing your SID and minimizing your OID. With OID, again, they show you how it plays a part in magnification or size distortion, because remember, size distortion can only be magnification. Shape distortion is elongation or foreshortening. So they're showing you with the OID, you've got pretty much the same SID, but one, you've got the part way up here, so there's all this OID, and this one, the part is lower, so there's still OID, but not near as much. But look how different the end result is. This is way more magnified because the OID is so much more here than here. So is it magnified a little bit here? Yes, but you've got less OID, equal SIDs. Less OID, less distortion. More OID, more distortion. This one is more magnified than this one, okay? And that is on the bottom of page 140 for reference. Now, there's another calculation that comes into play that we are not going to worry about right now, but I still want you to see that you can actually calculate the magnification size. So they tell you that the magnification factor is equivalent to your SID divided by your source to object distance. Remember that from the source to the IR is your SID. From the object to the image receptor is your OID, and from the source to the object you're imaging is your SOD. Remember, SOD plus OID equals SID. So you can calculate the magnification factor by taking the SID and dividing it by the SOD. And your SOD is a calculation where you take your SID minus the OID. And then your object size would be the image size divided by the magnification factor. And they give you all kinds of examples of this on page 141. All right, and they give you pretty much this particular image right here, and they tell you that if the magnification factor was 1, then there's no magnification. All right, but true object size, remember, is pretty much impossible because there's some amount of magnification on every single image. And if the magnification factor is greater than 1, then it gets expressed as a percentage. So they tell you if the magnification factor was 1.2, then the image size would be 20% larger than the object size, because 1 would represent 100% of the object. The 0.2 is 20% more, so it's 20% bigger than the actual object itself. All right, again, we don't have to worry about this math right now, but I did want you to see it so that you recognize that we could calculate how magnified something is if it was necessary to do. Like, it is possible, because anytime something is magnified on an image, the radiologist has to kind of give reason why, whether it was something the tech did on purpose, whether it was something that the patient couldn't help and they couldn't get closer to the board, or we were forced to do that. Or if none of those come into play, then we need to figure out, or the radiologist and the doctor need to figure out, why is that part so magnified? Is something wrong? Was there something wrong with the way we took the image, or is there something actually going on with the patient that is causing that part to appear as big as it is? Or is it really that big? Okay. And the last section of this talks about the central ray alignment. And we talked about with distortion that the central ray alignment does play a factor. These images are on page 142. And they tell you that you can, when you have shape distortion, it can actually occur from inaccurately aligning the central ray of either the tube, the part that you're examining, or the image receptor. And if there's any misalignment of the central ray among those factors, it'll alter the shape of the part and the way it appears on the radiographic image. All right, so when they show you picture A in this, right here, picture A represents proper alignment between the tube, the part, and the IR. So in picture A, remember I said that the tube is typically perpendicular to the part, perpendicular to the IR, and the part and the IR are parallel to each other. So this is appropriate. And if this is done appropriately like this, then this is what you visualize on your image. All right, so this is an elbow. It looks like an attempt at an external elbow, because typically on an external, it'll bring the radial head out into profile. It's not completely externally rotated, because it should free the radial head and neck and tuberosity from superimposition, but a pretty decent picture. In picture B, there's improper alignment between the X-ray tube, the part, and the IR. All right, so is the tube perpendicular to the part? Yes, but it's not perpendicular to the IR. And the part and the IR are not parallel to each other. All right, so in picture B, it looks elongated, meaning the part looks longer than it actually is. In this little one, now you've got the tube perpendicular to the IR, but the part and the IR are not parallel. So in this particular picture, it looks foreshortened. Okay, and then in picture C, you've got shape distortion, because the central ray is not perpendicular to the part, so it elongates the olecranon process in that particular elbow picture. All right, but remember, sometimes we do this on purpose. Remember I said we can use it to throw anatomy out of the way, or to unsuperimpose anatomy, because sometimes when you are imaging in the human body, parts tend to lie over one another, and there's not much we can do about that. We can only angle the central ray or angle the patient to try and throw the part out of the path of what we're trying to visualize. So sometimes it's done intentionally. It's not always an error on our part. Sometimes we do that in order to visualize the anatomy. All right, so that takes us through some of the factors that will affect our overall exposure on our image receptor. We do have the second half of that to look at, starting with grids, and that will be in part 2. But if you have any questions to this point in the lecture, I hope that you made note of those on the particular slides, or made a separate sheet, so that ideally next time we meet, I can go ahead and clear that up for you, hopefully. All right, and until then, I hope you all have a great day. Thank you so much.